ready to go. Mr.
We're on.
President, here's the firing pistol. Well, everybody, hello. It's our 243rd episode of this incredible, astounding Astronomy Club's weekly vlog podcast called the SBAU Astro Hour. Our club, is the Santa Barbara Astronomical Unit, headquartered up at the beautiful Santa Barbara Museum of Natural History. My name's Ronnie Herron, and this program follows up on a bi-monthly get-together we used to do on my local morning radio show years ago. Before I retired, and we took up all things cosmic, from nebulas to new stars, from black holes to Big Bang. And this week, the galactic gang on the Zoom screen with me is going to kick around these topics. Ladies and gentlemen, the summer triangle is sinking in the west. Goodbye, summer. Hello, winter skies. And then there's the cooling tower cluster, good old M29. For you folks who like an early morning shower, why not try the Orionid? It's a meteor blast reaching its peak as our moon reaches a new phase. And then, since our nighttime sky is pretty much moon-free, let's look for a nebula named after our golden state, shall we? We've got the spectral results this week of our interstellar comet visitor 3I/Atlas. And this week, we're going to get around to a science process called simultaneity. Time is not absolute. Last week, we ran out of time for time. And congrats again to UC Santa Barbara physicists John Martinez and Michelle Deveray, two of the three professors who won the 2025 Nobel Prize in Physics. The other was up in Berkeley. Could be interesting, guys, if we could try to book one of these guys, these gentlemen, as a monthly science speaker in 2026. But boy, we'd be entangled in quantum deeply. Let's meet the gang, shall we? On the screen, our beloved president, Jerry Wilson, after 7 years.
Good morning, everybody, and good morning, Joyce and Riley and Calvin.
And your wife,
Calvin's just back from visiting friends in Mr. Soda.
Yeah. Oh, it's not Minnesota. Okay. Well, do they watch us? Or...
Sometimes, yes. Mostly in reruns.
Well, I'm going to introduce you to Tim here in a minute. He checks for those messages on screen. Anyway, your lovely wife, Pat Forgy, is a believer, supporter of you, this club, and myself, and I love her. And I guess we lost Bruce because of the problem we had with his sound. Let's talk about the man to your bottom now on my screen, Chuck McPartland, the best outreach coordinator in America. Chuck is in
the universe.
Pretty much, yeah. He's in charge of the regular events, not the biggies, like our potluck and our Christmas dinner. He's also married to a neat sweetheart of a wife named Pat. Pat McPartland is merchandise manager as well as our treasurer. And we haven't been joined by Tom Whittemore this week. We lost Bruce Murdoch for a while, so we'll introduce you to Tim Crawford, who's like me, is a somewhat tag-along, but he knows his sky and knows his telescopes, and Tim is married to Karen. How's she doing these days?
Pretty good.
Did you bring her to the Filipenko speech?
No. She's probably in bed when it started.
Well, does she help you? Does she go out on events at night?
No, she did. She gets tired by 8 o'clock. Boy, she's crashing.
Well, let me go back to our outreach coordinator, Chuck. What's coming up real soon? We're into our third week here, I guess, of the month of October, right?
Yeah, pretty much just a school event at Kellogg School for their science night, which really isn't a public event, on Thursday. And then Friday, Saturday, Sunday is our camp out, so expect clouds and rain.
We already appeared at Westmont College this past weekend, right, Friday?
Yeah. Yeah, it was quite nice.
Rain is not going to happen, Chuck.
Okay.
Okay, well, it looks like the four of us on screen to talk about different things, but we start the hour off every week. We have for 4.5 years, and I don't know how the president does it. Keeps coming up with these things he forwards to us that are silly science cartoons. Some of them are thought provokers, and doggone if we didn't get a new batch of about half a dozen, 6 or 7 or 8 this past week. And here they come onto the screen, assuming the Zoom screen works. There we go. All right, that's a little small. I'm sorry. It looks like thought provoker. Oh yeah, you're going to have to explain this. The BS, is that bullpucky symmetry principle? You want to talk to us about this, Jerry? What is this
It
about?
says the amount of energy needed to refute BS, and we all know what BS
Sure, it's Bachelor of Science.
is an order of magnitude bigger than to produce it. One guy says, wait, I bet the moon's made of cheese. And the guy comes back, well, spectrographic analysis and orbit calculations suggest not. Plus, we built a rocket, took 3 people there, and they couldn't eat it. Then the guy says, yeah, I'm still thinking cheese.
And then you got the effort graph below them.
Oh, yeah. The effort to pop off like that and the effort to refute it.
Yeah, that's good.
They're also equivalent to attention span.
Yeah.
Are there people like flat earthers that believe there's cheese up there? Where did that start, I wonder?
I don't know. I've known people that claimed flat Earth when I was in high
I
school.
actually Googled it one time and I can't remember, but it goes way back. I think maybe late 1800s, something like that, or maybe
Well,
early
I'm sure it went
1900s.
farther back than that.
Well,
I think it came
Tim's
from
talking cheese.
I think it came from a poem. I'm not sure though. I can't remember.
Well,
Really?
people call the remote areas of the Earth the 4 corners of the Earth. So spheres don't have corners. But the people I knew in high school that did it, I knew they were joking. They were doing it just to confound people.
Yeah.
So I don't think there are real flat earthers.
Well, Tim was talking about the cheese people.
Oh, the cheese people. Yeah.
Yeah. I can actually with the kids when the kids come out and I got the moon up, I get a really really bright green filter. And I
Yeah.
said, "Do you think it's made of green cheese?" And they take a look and you're going, "Whoa!"
If cheese is green, it's bad, hasn't it? There is no normal green cheese you
It
can eat.
depends on the cheese.
I guess so. You're right. This bicycle is on the screen. It's called the Relativity Special.
Oh,
You
yes.
pedal at 90 RPM, designed to travel faster than c squared. That's the speed of light.
No, not the speed of light is just C, Ron.
Okay, so you multiply 186,000 miles an hour times 186,000. What do you get? An incredible number. But this sucker has 12. What are those called? Spikes?
No, you get the same number.
Rockets.
You know what?
1, 2, 3. Welcome back, Bruce.
Hi, Bruce.
1,
We're
2,
not-
Am I now?
6, 7, 8, 9,
No echo?
11,
We're not feeding back. Doesn't sound like there's a delay, my friend.
11
read?
sprockets.
Okay, one revolution of the pedals on this bike.
You did, I am feeding back or not?
No, we're not. It's our voices that come back. We had a little problem before we signed on, folks. But you want to talk about this, Jerry? Talk to what
Well,
we're talking about.
Yeah, it's got all these chains and gear wheels, and as you know, they amplify motion. So this is an ultra high gearing that with those gear combinations, and I don't know that it actually mathematically is right, but on the gear ratios, one revolution of the pedals, the bike moves 6 times around the Earth. Unfortunately, it makes 7 times around the Earth to equal the speed of light.
Okay.
It's part of the art exhibition Circle of Time at Pat Chiraparvati curated, California State University, Sacramento. So I would guess this was done by a physics class.
And you think it works? I mean,
No.
it doesn't go the speed of light, but does it go damn fast?
If it went with that gear ratio, it would take you forever to pump that. You'd have to pump the pedal, the main pedal, at an incredible speed to get any kind of motion out of it at first, or you'd have to really push on it to get going.
Yeah, huge amount of effort. Yeah.
Is there a word that I'm missing? What are those round cog wheels called?
Gears.
Yeah.
Oh, is that a gear? That's all it is.
Or bike sprockets.
Okay, brake sprockets. All right. Okay, we're inside the scientist's lab, and his AI is talking to him from the computer saying, there was a typo, doctor, in my previous email. It should, of course, read, please focus completely on genome, not GNOME or GNOME research. Left out the E.
No.
That's right. GNOME is spelled with a silent G, but
But it looks like he's made progress on gnome research.
Yeah.
that's true. He's got them. Little gnomes are everywhere. Now, this was a painter, complete with easel, brush, and paint. And he was painting what he was seeing in the last minute before he was sucked up by a laser beam. And he's no longer with us. We get it. He's a fast painter if he got that much.
by an artist named Twonks.
Yeah. Oh, okay. Having a. All right. Now this needs some explanation.
This
Trick
is a
and
logic
treat.
diagram.
What is it? What kind of diagram?
It's a logic diagram with Venn diagrams, but it's logic.
Okay, but why would they mean these things they do that we just change the middle word?
Well, if this one is trick and this one is treat, then this is trick or treat, and that covers the whole area. And this
Okay,
is trick and treat, so it only covers this area.
okay.
This is trick.
XOR.
Yeah.
OR.
Someone else will have to explain this. I'm not familiar with the X thing.
Exclusive or.
Okay, exclusive or. Thank you. That makes sense.
Exclusive or.
Yeah. And this is trick nor treat, so neither one, nothing.
Okay.
So this is trick NAND treat. So this is not and, so it's the opposite of trick and treat, which is there. And this is trick exclusive not or treat.
And this is all based on something from geometry or mathematics?
Oh, it's logic, Ron.
Boolean algebra.
When you build a circuit to do a logic circuit, these are the rules that you use to wire it up.
Oh, okay. I loved the logic class I took at my college.
Oh, you get a really complicated circuit, it can drive you nuts.
Yeah, I'm sure it,
I'm an example.
a lot of it makes sense.
It does make sense.
Now this one definitely you're going to have to tell us. 404 mathematics lab. What does that mean? What's the connotation there?
Means you can't find it.
404 means you can't find something?
When you went to a website that your computer can't find, it said 404, error, cannot find.
Really?
Yeah,
Why those numbers?
I have no idea.
You don't know. 404 means not
The
available.
Braille says 404 also.
The what?
The
Would you
Braille
screw-
also says 404.
What's
Yes.
that? What?
Yeah, the Braille also says 404.
Oh, is that what that is in the middle? Oh,
Yeah, Braille.
Probably says something like room 404.
Yeah.
so they're going to
Yeah, I don't know if the first character is.
Yeah.
Isn't 404 not found on the computer?
Yeah.
Yeah.
going to be like level 13 on the elevators. They're going to leave it out and go right to the 14th floor. Okay, astronomy
if you are in an elevator and you see floor 13, get out. You're in a horror movie.
You want to guide us through this one, Jerry, or somebody else?
This is the one that I sent out to you, an email that somehow didn't succeed in sending.
Oh, we got it.
Yeah, you got it now.
Oh, okay.
I remember this one.
Yeah,
So this is a little checklist of all the planets
that have rings.
that have rings. And now recently, Earth has joined them.
Huh.
It has
Oh.
stationary
I can-
satellites.
Yeah, okay. That's the one I didn't see.
A
Okay.
century ago, Earth didn't have rings, but we have one now. It's where all the satellite dishes are pointed.
And that's,
We not only have rings, we have a sphere.
We have that too, much closer in, yeah.
but the word should be geocentric.
And they're not all in a stationary orbit either.
Well, some of them are over the
Not all the
North Pole.
close ones, no.
Would that ring exist above the equator?
No, the disk is, the disk is above the,
Equator.
it's above the rotation axis, 90 degrees from the rotation axis, yes. And it's not a
Yeah,
complete,
Satellite dish pointed at the sky is always it always points to the same place because the
yes,
geostationary orbit has the same orbital period as the rotation of the Earth.
Yeah, all these planets, all the gas giants have it above their equators, don't they? It's turning in the
well,
middle.
they mill around too. Their orbits aren't exactly stable permanently.
But the space debris stuff I've seen before just shows a big buzzing beehive.
Well, this isn't debris. This is showing geostationary satellites, which is a really popular place for communication satellites and
23
TV satellites.
The one you see
22,000.
that's all around the Earth is the low Earth orbit, right tight around the Earth 200 feet or 200 miles up.
200 miles. 200
Yeah.
miles, you mean?
What's that?
Yeah, this is 22,400 miles up.
Yeah, this is
The
the
geostationary belt is
the lower orbit is 200
22,400 miles up.
Imagine most of them are above our continent up here, aren't they? Our United States.
Now, most of Elon Musk's satellites are in low Earth orbit out here. And when the sun has a lot of activity on it, it activates our atmosphere and causes the atmosphere to swell a little bit. And that increases because his satellites are just above the significant part of the atmosphere. And so when the atmosphere swells, it puts extra drag on his low Earth orbit satellites. And he will lose up to 200 per year because of solar activity like that.
Really?
He's actually deorbiting about 5 a day now.
Yeah.
Well, you gentlemen have all heard of those sci-fi based space elevators.
Yeah.
And there's
Don't
some
look for that soon.
well, they would go up to this ring, wouldn't they? They wouldn't just go up to a passing ISS. They'd have to go to something that's stable and stuck there.
Yeah.
23
we had a gentleman that came and talked to us about
yeah. I forget who that
elevator.
was. And what's out there among let's see, XM, Sirius XM is out there. What else? Don't we get our GPS from passing satellites like Elon?
Yeah, but they're not in geostationary orbits.
I know.
Yeah.
Would it take a little longer? You get a little delay, right? From a geostationary.
Quite a bit.
Delay.
Speaking of delays,
This is not one of the cartoons, unless I missed it.
No, we're into the talk.
Okay. There is a graph from hell, ladies and
But
gentlemen.
this one is easier to start with.
Okay, B was first.
This is about simultaneity. And this is a Gedanken experiment, which means it wasn't actually physically performed. It's just logical consequences of situations that you can think of. And this one is for one person. See now, this guy is standing here and he's standing still. And he sees two lightning flashes right here. And in his world, A and B happen at exactly the same time because the flash from the lightning travels to his eyes at the speed of light. And if he's accurately placed between the two flashes, he will get the flash from A and the flash from B at exactly the same time. But if this guy who is traveling on a rocket ship and he happens to pass over this guy at the time that these two lightning flashes happen, which are simultaneous for him, the light from this one will get to this guy first. So he won't see it because he's running away from this light and he's running toward this light. So he will not see them simultaneous. He will see them, he will see this one first. See, it says B was first. And here he says same time. And this is a V for vector velocity. Now, what this shows is that time is different depending on what you're doing and where you are. This is the what you're doing issue. It's the difference between the two things is speed. And this guy up here on the rocket, he has to be traveling at a very high speed. You know, the regular rockets of 18,000 miles won't notice this effect. But traveling like half the speed of light, he would notice it. So this disproves.
It'll also be blue shifted.
Well,
Didn't get that, Bruce. Say it again.
It will also be blue shifted in spectrum.
what does it stand for?
The
what?
The lightning flash will look more blue to him.
Yes.
The lightning flash will also look more blue.
Yeah, you're right.
That's
Doppler
the
effect.
opposite direction from infrared.
Well, infrared is.
Well, if there's lightning flash on A, it would be red shifted.
Yeah.
But he's going toward B, so he's compressing the light waves there, so they'll be blue shifted.
Okay. But let's not get too far off the beaten path here. The issue here, the thing it does is this proves that this type of thing proves that time is not absolute. And in Newton's time, when Newton came up with his laws of motion, he assumed that time, implicitly, that time was absolute. And so he gets none of these relativistic effects. You'll only get these from the Gedanken experiment that Einstein mused on, and this is one of them. The other key one that he mused on was, what would a person in a falling elevator see? Would he, because he'd be weightless, and how would he feel? What's his frame of reference? And he started looking at these things, and he decided that not only is the speed of light constant to make this work, but it's velocity dependent, what you see. So there is no simultaneity for any frame of reference. Being simultaneous is in a specific frame of reference. And this is like what I wrote, I think, 2 newsletters ago about GPS figuring out where you are now. Well, the GPS is this guy in the rocket, and his now is different than the now on the guy on the ground. So to get your GPS to work accurately enough for it to be useful, the satellite has to figure out the difference between the now at the satellite and the now when you press the button and ask where your coordinates are. So it has to do a general relativistic calculation to figure out the difference in nows to correct for non-simultaneity. So
Jerry, with those differences, if you're in a different GPS location, is that instantaneously computerized from the satellite?
Nothing instantaneous. It takes time to do the computations.
Well, can I ask a question? Is there any way this could be portrayed like they do the old train passing?
That's the other experiment.
I know, but that's sound, and that's lower. That wouldn't be connected to this side.
No, this is analogous. If these are sounds, then these are 2 trains. One is going this way, one is stationary, and
this one I got confused.
Yeah, so this is and these trains are traveling at half the speed of light, say. But if you take a sound analogy, it's exactly the same. So because the lightning, in this case, you're not looking at lightning flash, you're listening for thunder. If you're moving because the speed of sound in the atmosphere, assuming it's constant, because the speed of sound actually depends on density, temperature, and humidity. So if you make all those equal, then it becomes analogous. And this is the speed of, so for these lightning flashes, this is the speed of light moving in this frame toward this observer, and you can see it's equally spaced. But this guy has already gotten to the wave, the frontage wave for the light wave, so he sees it first. Now the guy that's stationary, he sees it simultaneous. And this other guy down here, he's speeding away. Now he hears the other one, and it's anything but simultaneous. So these are the two differences that had to be taken into account to produce the theory of relativity, special relativity and general relativity.
And your comments about orbiting satellites like GPS or whatever that have to make allowances, what are we talking about? A second or 2 difference? Their time is that much slower?
It's more like hundreds of feet on the ground. I don't recall the time difference, but it would make your GPS useless for your navigation.
It's probably going to be nanoseconds or seconds.
Yeah, probably that.
1 foot per nanosecond.
Now, the 2 effects that affect your GPS is that one, the satellite is farther away from the Earth than you are. So you are in a stronger gravitational field than the satellite is. So if you're near, so for the observer on the ground, your time slows down. And the satellite is moving faster than you are. You're moving at 18,000 miles an hour on the satellite, but on the ground, you're only moving somewhere around 600 miles an hour for us. So the faster you go, the slower your time goes. So these 2 effects do not cancel each other out. And so you have to correct for each of them in order to get this right.
And that whole process is the spontaneity. What is it? What is that?
the lack of simultaneity in this case is symptomatic of the fact that time passes differently, that there's no absolute time.
And the ultimate version of this is going at near the speed of light to Andromeda, and you age, what, a few minutes?
If you get, in one thing I wrote that if you're doing 99 point, and I think I put 5 nines after the decimal point, but it actually needs closer to 17 nines after the decimal point. But you would only get from our observation point here in the Milky Way, you could get to center of Andromeda in a few minutes if you traveled at a significant fraction of the speed of light. Of course, in getting there and then coming back, you might get back within the hour, but you've passed time of 5 million years has transited on the Earth.
So we could take a look at any one of these passengers going at that speed. They'd be in a suspended animation. It'd be like something you see on TV that locks up. Occasionally my face does that on the screen. It locks up.
The guy, if the guy down here is observing this guy, and this guy is traveling fast enough, he would appear to not be moving in his frame. If you watched his clock,
wow,
you would see that his clock is not moving. And if he was watching your clock, he would see that 2.5 million years passed on time it took you to get to Andromeda.
So, just an aside, Richard noted online that he likes the idea that you're using this experiment with sound as well.
Yeah.
And I told him that the pitches are going to be different as well.
Yeah.
Compressing and going further away, they go higher and lower.
Yeah.
So that's analogous to the color of the light that Bruce mentioned.
Yes.
Right.
What is that? What is that effect called? I can't remember it now for some reason.
Doppler effect.
Doppler effect.
So these guys are seeing a little bit into the other's future or the other's past. So this brings up the philosophical point that the present does not disappear when it's past. There is a past that is extant. There is a future that is extant and in other frames, and you can see into those, even though the person in that frame can't.
Wow.
But we're not going to go there.
Yeah.
Okay.
We're going to go to the night sky instead.
Oh yeah, go back to that other cone, light cone.
One last
This
thing.
is the way you would represent it in the light cone in special relativity. A and B are simultaneous in the green reference frame. B occurs first in the red frame and later in the blue reference frame. What that shows is that velocity is a rotation from space into time. And as you rotate by the speed of light, you get into a position where time does not pass. It's all spatial. So a photon, if you could put a saddle on a photon and ride it, you would arrive at your destination at the same instant you were emitted by the source. Time would not pass for a photon. Now, this stuff for me was very difficult to appreciate when I was taking this as a junior level undergraduate in physics. I thought this stuff is crazy. And then I realized that I had to understand crazy if I was going to get anywhere in physics.
Well, speaking of crazy, Mr. President, I once told you that it felt to me like time went through we went through time, or time itself travels at the speed of light. And you said I was crazy, and I guess I am, but that seems to me make sense. Time is going through everything at the speed of light. If we stop and slow and let it go past, then
yeah, I don't like that time travels at the speed of light. Time doesn't travel. When you go the speed of light, time stops.
Well, that's because, okay, you're right. It doesn't make
There's
sense.
this little annoying factor that shows up all over the place, which is the square root of 1 minus v squared over c squared.
Yeah.
Where c is the speed of light and v is u.
Mm-hmm.
So as v and c become the same or nearly the same, that quantity shrinks to like 0.
Well, everybody knows that, Bruce, for crying out loud.
Yeah, we need a whiteboard to go over that stuff. So anyway, this is looking at the what are we looking at here?
Summer Triangle.
Summer Triangle. Oh yeah. So here we are with Altair, and this is setting in the west. The horizon is just out of reach here. There's Hercules down there. So Altair, Vega, and
To the right, Deneb.
Deneb.
To the
I
right.
can't find the word Deneb.
To the right.
right,
There you
right
go.
there.
Yeah. Yeah. So that's the Summer Triangle. It has a lot of the Milky Way in it. This is the core of the galaxy down here near Sagittarius. And this is all, these are summer constellations and they're disappearing. And we say hello to the winter constellations, which have all the bright stars in them. Not all the bright stars.
This must be from Astronomy Magazine. It's getting low, so let's look at it.
Yeah, yes, right. They pull that.
That's good. I like it.
Is that the reason they call it the Summer Triangle? It disappears in winter,
Yeah, it's not seen in winter.
and few other things do that. Aren't there a whole bunch of
No.
stuff?
What they
Well,
do.
Orion does that, for example. The other way around, though.
Sometimes I've caught astronomy putting pasting paragraphs in for the wrong season.
Yeah.
So I know what they do is they paste something in from the wrong season, and then they say 6 months from now we'll see, and then they have, so they don't have to rewrite a lot. This is M29, known as the cooling tower cluster. Do you see a cooling tower in there? I don't.
I
No.
don't even know what a cooling tower is.
Definitely something we don't need in
It's
this winter.
those things in at nuclear power plants where they look like a concrete hourglass.
Oh, sure. Okay. Yeah, no, I don't.
That
You
kind
can
of
sort of, it's tilted a little, but you can
Yeah.
sort of see that. But
Maybe
yeah.
there and there.
Yeah.
Are there only half a dozen stars in this?
Really obvious ones.
Okay.
Yeah.
Tom, tell the
It's
listeners,
hard to-
space launch right now?
No, that was from yesterday.
Yeah.
Oh, okay.
Now this red here on the side can drive you crazy in processing if you think this is not real. And sometimes errors in processing look like this. But this is dust in the Milky Way. And because of this dust, it makes it changes the apparent magnitude of these things in an unknown way. So the distance to that has not been well calculated. The official value is 5,240 light years, but the high reliability is between 4,000 and 7,200.
Very close to a mile of light years
Yeah.
in feet.
Amazingly enough, your little dinky Kircher turned into a beautiful hand that I could see very well in that case.
Oh yeah.
Why doesn't it stay that way? Now there's on the side, it's the cursor again.
I'd have to ask God. Don't ask.
Now it's a cursor.
It's magic.
Mhm. Okay, now this is Orion. This is the winter constellation with a lot of bright stars.
Right.
Leo's down here. Taurus is up there. And this is roughly placed, could be anywhere in here, roughly the radiant point of the Orionid meteor shower. So you want to look over here and over here. If it's not impossible, but if one came directly at you from the radiant, it would not move spatially. It would just brighten and then disappear, unless it brightened enough, and then it would hit you.
Really?
But
You guys have actually taken videos of stuff like that? You've seen meteorites?
Well, if you look at it in spherical coordinates, your brain has an excellent algorithm for deciding on possible collisions. If you're sitting there looking at something and someone at the edge of your field of view, say 90 degrees away, winds up and throws a baseball at your head, you will immediately do this because your eye spotted the motion, but it realized that there was no angular motion. There was just the thing was getting bigger. And so that means collision course, and all sorts of alarms go off in your head. Now that's also the guiding technique they use for air-to-air missiles. Collision course is defined by tracking it so that there's no angular motion of the target. It's just radial, and then it just waits.
But I'll bet you there's been some astronomers in the past that thought they were seeing a supernova happen.
Too fast.
Yeah.
Too fast, so they don't blow that fast. I guess you're right.
So anyway, it should be a good one this year. Right now, the moon is new or about new. And so if you're up between midnight and 6 a.m. tonight, you should, it's October 21st, tomorrow, you should see a good shower.
I didn't see any this morning.
You what?
I didn't see any this morning. I was out there at, 4 to 6.
Yeah, okay.
I was out there about 3 a.m. and I didn't see any either.
They're saving them up for tomorrow.
Yeah.
Now
Pieces
it's
of Halley's Comet.
Uh-huh.
Okay, there's a number of comets. I think Swan and one other one are passing their closest path to Earth today.
Lemon?
Lemon, yeah, that's it.
But we're visiting that interstellar visitor.
No, we're getting to that.
Oh,
That one went by Mars a couple of days ago.
Here at 10 o'clock in the evening, tomorrow, this is, what are we looking at? Oh yeah, this is the California Nebula down here. And this is the constellation of Perseus, AKA the running man.
The lawn chair.
The lawn, oh yeah. That's the trouble. This program won't let me rewrite these red lines because I really don't like these. Their choice of pattern is arbitrary.
It looks like they used a lot of the one from H.A. Ray.
Huh.
That kind of wrote the kids' books with Curious George. He also did a constellation one.
Oh, I didn't know that. Okay. Anyway, the down here next to Menkib, right near it is the California Nebula. It's big, but it's faint. And this picture is a composite of two frames because it is big, and this is several degrees apart. So your typical frame in amateur telescopes is around a half a degree to a degree, depending on the scope you use. Now, these new things that are out, the
Sea stars.
The sea stars, yeah, they have smaller lenses, shorter focal length. So you could probably fit all of this in one frame with one of those. But talking about things like 5-inch f5 refractors, it's going to take two frames. Do you know the F number of the sea stars?
They're F5.
F5, okay.
I think you'd need the C star 30 to see this all.
The 30, yeah.
It can fit the Andromeda Galaxy.
Okay. Yeah, it's a beautiful thing. Now I think it's magnitude 6 overall, but that's taking all the light from the whole thing and computationally putting it into a point source. Then the star would be magnitude 6. But spread over this big area, you're not going to easily see this with the naked eye.
Now, Jerry, in your talking points, you mentioned a hydrogen alpha filter. That's not for visual. That's for imaging, correct?
It's in the extreme red. So I would assume that's for imaging. I use
You want an O3 filter for this.
What's that?
You want an O3 filter for this.
Yeah, I would
O3.
use that.
Okay.
H alpha if you are taking an image. And H alpha has real advantages for being in a city because there's almost no light pollution at hydrogen alpha wavelengths. So even on hazy or light polluted skies, you can pull out all sorts of detail. It does take long exposures because there's not much light in that band. It's very narrow.
Do sea stars use that?
No.
Okay.
No, they're broadband.
But you
Okay.
can screw one on. Now this is the Comet 3I Atlas. It is not a starship. It is not a technology.
We think.
When 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 Avi Loeb speaks, he is talking, as scientists do, about possibilities and not probabilities. We all look at probabilities. This thing does not act like a spaceship. People claim it's showing now an anti-tail, and people are saying, well, that's a retrojet, it's slowing down now.
Yeah.
Well, that's just the amount of scientific illiteracy in this country just stuns me. It's breathtaking.
But the earlier one we saw, Oumuamua, we knew the shape of it. This one, it's buried inside that gaseous cloud, isn't it?
Yeah.
Yes.
Yeah, the shape of this has been estimated, or the size of it has been estimated several times. I don't have the number at my fingertips, but it's in the talking points somewhere.
But it's not a cigar.
No, it's not a cigar. And Oumuamua wasn't a cigar either. It was either a pancake or a cigar. So you could look on it as a Frisbee if you want.
But they said it did some strange things leaving.
They said it changed its course, and that's normal for a comet. That's why comets are so hard to track, because they, as they rotate, say a pool of frozen CO2 will now come into the sunlight on that thing, and the sun will heat it up and it will vaporize and it'll shoot gaseous CO2 off into space. That's a rocket engine. And so that'll move the comet away from in the direction the tail is not. You know, it'll change its orbit slightly, and enough of these happen, it'll do. And that's what happened with Oumuamua. It started boiling off volatile gases, and it changed its slope or its trajectory, not because anyone's on there trying to get a view of Earth. So, and it didn't come close enough. And this was only out at the position of Mars somewhere.
I have a question for Chuck here. Chuck, is it possible to use this like you do with asteroid occultations to find the shape of this?
There is a Comet Ox feed for occultations where people try to get occultations, but they tend to be fast moving, and you have to, there's effects from the coma too.
Okay.
And so you don't have a good position for the actual nucleus, so it's harder to predict an occultation.
Okay.
Well, are you talking about the comet we're looking at is the occulter and an occulter star, or something goes in front of this?
Yeah, go ahead.
Any comet going in front of a star.
Right.
Why, really?
Oh, this had to be a relatively short exposure because the comet isn't smeared with respect to the background stars, either or.
No, this is a picture that I would guess is a composite of the comet, tracking on the comet, and then tracking on the stars, and then the two combined.
Put them together, yeah.
Last Tuesday at our workshop, we were discussing how to do this, and Chuck Watson came up with the best way to do it. And that is you take a picture of the star field that the comet's going to be in, and then you take a picture of the comet in that star field, and you erase all the stars, and then you put the two together. We call it the Watson process now.
That's good. That was a cool one.
Yeah.
You can see there is some smearing of the stars, and this is from a really big telescope, so
Yes.
it might just be one exposure.
But, well, then you get these diffraction rings, I mean spikes. And those generally disappear right away if you get much star motion. But you're right, the stars are not circles, they're little footballs.
Well, if you could make that square we're looking at like a clock, that little short tail on the comet is pointing to 8:30. Does that mean the sun would be at 2:30 on the right side, slightly up?
Sun's right up there.
Yeah, in other words, most tails on comets, not all of them I understand, but most are simply going with the solar wind, aren't they?
Yes, they point away from the sun. Now the comet could
Well,
be
there's two
moving
tails.
this way.
Comet
There's two
what?
tails, the ion tail and the dust tail. The dust tail points in the orbit of the comet. The ion tail points toward the sun, or away from the sun.
Yeah,
Oh.
they claim this one now has an anti-tail. And they claim that's because the comet is maneuvering and has turned on itself. And that's just BS.
But why would it have Why would it have a dust tail? There's no friction that doesn't run into anything.
It's got a lot of dust. No, it blows off its own dust.
Really?
Yeah, it's like a little gas explosion going on there to
Yeah.
form the tail, and that blows off dust.
The CO2 in the water ice is not pure. It's got dust mixed in with it. It's like thin mud.
I'll be damned.
Yeah.
And this is eventually going to go away, right? Leave
Yeah.
It's going to leave the solar system.
soon, or we got years to see it?
No,
Relatively
years.
soon.
Couple months, it'll be gone. This is
Gone
Thompson.
forever.
Go merge with Oumuamua and get the fleet back together.
So this is its
Where are we?
magnitude. This is a magnitude scale 15, magnitude 15. Actually, this is about 14 and a half. And this is magnitude 22, which is 21st magnitude is about the farthest you can see with telescopes from Earth for a long time until they got these super giant ones going 8 and 10 meters and multiples of them. So that used to be kind of a barrier. These are the estimates of its brightness with error bars on it. And then you can see that as things got a little brighter, the error bars got smaller, and now they don't need much error bar. And now we're getting into a lot of people can do it. And this is, so the actual value is probably somewhere in here. This is since discovery. I don't know if this is since discovery, I believe, and this is since then. And this is, they found it on old plates and estimated. But this is from this data, the black data is from TESS. This is the first observatory MPC. I'm not sure what that is.
Minor Planet Center.
Okay. Discovery on July 1st, 2025. That's a line with 2 dots. I'm sure it's in there somewhere.
Yeah.
And this is, anyway, this is a number of estimates in different colors. So these are different spectral bands in here. And that leads to the spectroscopy of it. But this is the path of 3I Atlas. And here we are down here in May 2025. And June, July, August, September, October, right there, we're there, 20, right there. And it's above Spica. And then we're going to go up here. And in March 12 of this year, it's probably going to be disappearing.
Spica is not really visible. I mean, it sets pretty early.
Yeah, for us earthbound things, yes, but that it's still near Spica in the sky if you could see Spica.
That's near the sun in the sky, so
Yeah.
Yeah.
Comets always do that. They're very irritating. They're either too near the sun or they're in the south.
What's this?
This is a picture of the orbit of 3I Atlas around the core of the galaxy. Now it's leaving the solar system, but it's not leaving the galaxy.
Well,
So that one and the next one. This is a side view of its orbit in our galaxy. And our galaxy really does look like this. It's warped. And it's got a bar in the middle. Yeah. Go ahead.
Frisbee.
The yellow line, if you can spot that in there. The yellow line is the orbit of the sun. The red within the Milky Way galaxy is 3I Atlas, and it has a tilted orbit slightly that brings it farther above and below the galactic plane than the sun, as shown. So this red one, that's the comet, and this yellow is the sun. The sun goes above and below the galactic plane, but not by much, not like the comet does.
and this is, 250 million years worth of orbit here.
Yes, exactly. Now this is looking straight down on it. Again, the yellow line is the sun, and the red line is the calculated orbit of that comet. And this, as Chuck points out, each circle is 250 million years. So this is about 1.5 billion years
Holy mackerel.
orbit. But it's not going to meet that because, like we just talked about, it adjusts its orbits teeny bits all the time. And that's why they're so hard to predict.
Plus, it went by the sun, and that's going to twist its orbit a little. And
Yeah, that's right. It's going to do a little, what do they call that? Planetary boost.
yeah.
It's flyby shooting.
Couldn't
Well,
it be
the guy that collected this is really old.
Yeah.
couldn't it be captured someday by a stellar system and a couple?
If that's harder than you might think, it takes a total combined of 3 stars, 2 stars to capture a third star or a third object. One star can't capture another one. If it comes roaring in at a hyperbolic trajectory, you've changed the hyperbolic trajectory, but it's still hyperbolic.
Yeah.
If you want to capture it, you've got to tangle with 2 stars, a double star, and usually one of the other stars will take off on the hyperbolic orbit.
But
These are all fun celestial mechanic combinations that we do in junior level mechanics. And
chances are these interstellar visitors have been coming through our solar system all along, but only
absolutely.
recently have we discovered. Did it start with Oumuamua within the last 5 years?
I think there was one that was classified before that.
I think they discounted that one. That was another Avi Loeb looking back through data.
Oh, okay. Thank you.
But
I've got it.
obviously, what did we call them before? Did we just lump them in with our own comets and think they were going around the sun in the past?
We didn't see them.
Couldn't see them. That's what it is. I have a feeling we're going to see a lot of them from now on.
Well, we're
Looks like
getting
the
better at
Pringle
detecting.
galaxy.
Would you say, Tim?
That looks like one of those Pringle chips.
Yeah.
Yeah.
Someone made a comment about that, and I said that reminds me of on the internet once they had a potato chip that was shaped like Jesus.
Oh God.
And someone corrected me and said it was a toast.
Yeah.
That's right. Yeah. Jesus and his
Anyway,
people gather every year around that toast.
so this is a wavelength in microns. This is 1 micron. So that's primarily dust we get. The light comes from dust. This is short IR wavelength. It's long visible wavelength. When you have a camera, CCD camera on your telescope or a CMOS, they both use silicon. The silicon is sensitive out to about here, about a micron in the near IR. But cameras all come with a blocking filter to block the IR. If you remove that blocking filter, then you can never get focus with a refractor on it because the wavelengths don't come to the same point. But in a reflector, you can see this part of the spectrum here.
Jerry,
Yeah,
Richard online wants to know, do we think it is that 3i has made a full orbit, or how many orbits do we think it's made?
there's no way I should tell that
Okay.
I know of.
Sure.
Out here in the infrared, you start getting H2O, for example, H2O ice, CO2, 13 CO2, and CO. So this is H2O ice in here also.
I've seen an estimate for the age of the comet, and that was 9 billion years.
Yeah.
So you could kind of, speculate a couple of orbits from that.
Yeah, if it's 250 million per orbit,
Yeah.
you take 9 and multiply it by 4, and that's potentially how many orbits it's made.
Okay, but thank you. That's good. I hope Richard got that. Yeah, that's great. That's good info.
Oh, this shrank. There we go.
These are emission lines at very long wavelengths. Let's see, it doesn't give the,
It needs more contrast.
oh, sorry.
And it does say ultraviolet B.
Yeah. It depends whether these are angstroms or not. If these are angstroms, then this is the ultraviolet. UVB, yeah, it's ultraviolet. Okay, let me get more contrast.
Wonder why the big thick one in the middle doesn't go left. Okay. We're still on our interstellar visitor here.
Yeah, he's magnifying the contrast in the plot that he had.
Is that better?
Yeah.
A lot better.
Okay. So in the ultraviolet, there's a lot of stuff out here with continuum extracted in the UV. So there's a lot of structure out here. It's not identified as to what it is, at least on this thing. The caption on the picture, if you could read that. It's emission lines caused by atomic nickel. And the right panel shows weak emission lines caused by cyanide gas. These emission lines grew more obvious over time because 3I Atlas is becoming more active during its approach to the sun. So this is the C up here. There, this is the CN band. And this is the nickel stuff. Nickel lines are the dotted lines here, nickel lines.
Nickel.
So it has a lot of nickel in it. At first, it had no iron in it, which is drove people nuts. It's obviously a polished spacecraft made out of nickel.
No, I don't see the dotted lines.
Oh. There's a dotted line right there.
Oh, okay, good.
And here's two dotted lines together.
Okay.
So
And they're on those peaks.
this, yeah,
All in the ultraviolet range.
yeah.
Well, does it not appear in the infrared?
No, the infrared we looked at before, that was showing the CO2 and the H2O.
Oh, that's what that was. Okay.
Now, this is a nickel production rates versus heliocentric distance comparison with solar system and interstellar comets. And these things are 3I Atlas, these with error bars. The black, I don't see that. Oh, the black is the weighted fit for that. That's how it's characterized. And the dotted line is an unweighted fit. Interstellar objects are 2I Borisov, and
Oumuamua?
I don't see Oumuamua.
Oh, they didn't do it. Okay.
And the
Stop
Jupiter
giving them
family
names.
comet. The Jupiter family comets are here, 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 here. And this one is titanium. And external comets are this, this, and this. So this is kind of a scatter plot, but it shows the neighborhood that 3I is in. And this is how it's behaving. As it closes the distance, it comes in here. What is Mars is around here, so that's as bright as it's going to get.
Yeah.
Now this one characterizes our own long period comets, the circles, Jupiter family comets, main belt comets, these two, and centaurs, this one and this one. And this is 3I Atlas, and I forgot what this one is. But it's a little different behavior in distance for the 3I Atlas. It's definitely a different composition. It's got the signature of a different solar system. Okay. Oh, we've only got two minutes. Okay, we're changing here to now to astrophotography in answer to what Tim had last time. This is a picture of the screen from CCD Stack 2, and it shows the picture of a star as taken with a DSLR camera. It's called Canon RAW. And you can see that the star is not represented uniformly. It's either a red or a blue star, and where it's dark in there, that's the pixel for the other color. If it's a red star, then this is a blue pixel because it's not picking up enough light or anything. And this shows you the background in Bayer filter unit cells. This is after debayer, and this is how you do a debayer. You interpolate full size. So this one is to produce a red, reassemble to red. So this is to convert to red. It's not checked, but I would check that. Oh, it's a grayscale. So they're interpolating the red, green, and blue into a black and white picture.
Okay.
So, and this is the proportion of that color that it assumed to have. So when you get to the end, when you have a red, blue, and a green picture, you put them together with this weight, and then it will produce what the camera saw. Now, every Bayer pattern at that time had one of these patterns, and it starts, all focal planes are labeled from upper left to lower right, just like your TV screen was when it did a raster scan. So the top left picture is red, then there's 2 green pixels, and then there's a blue. And this is the way Canon does it. So this is pressed to use for a Canon camera. And this was apply to all. And then this is the result over here after it does the debayer. This is a black and white picture. The star is now represented as a black and white picture. It's resampled all these pictures to put the light together into white. And so that's the picture you get. Now,
Are the black specks, are those need
Noise.
to be, they're noise?
it's a fixed pattern noise or a background noise.
And is that why you do the black, the dark frames?
Yes, but you apply the dark frame to this frame because this is what the camera took, and this is what you screwed up. So now I do a dark black pixel map, and I have every one of these dark pixels replaced with the average of the nearest 4 neighbors, and so
interesting
background. And then, just taking a few minutes here. This is the effect of stacking. This is just a picture on the frame of this is looking at a red frame, just red pixels, and these are the options it gives you. You can add up each exposure, but then you will exceed the brightness. It'll saturate things. The mean, which is what I use, a simple sum plus divide by the number of frames, so it normalizes it to prevent saturation. And that's what I do. So you pick that, you pick mean, and then you go. And then, whoops.
Oh, darn.
Back to the beginning.
This one doesn't do well on this.
Yeah. But
Well,
you do have a result. So that.
I think we'll be doing a 3-page report from Tim Crawford by next week on this.
So, well, no, this just takes a minute. This is using a mean, combine, and division. This is a single frame, a subframe that is 5 minutes long. And this is the stacking result of 12 of these 5-minute subframes. And you can see there's no star there, but there is a star there. So it increases your contrast and your dynamic range, and it increases your sharpness.
That's really impressive.
And this, you could get this if you took the picture steady for an hour, but you'd have airplanes and satellites and all sorts of crap through it.
It's a Pringle.
It's a hamburger.
Yeah.
It's a hot dog.
Oh, I guess there's no set length on any YouTube video. We can go as long as we want, gents. Man, oh man.
That's true.
Nice, Jerry. I like it.
Might want to revisit that topic again in the future, gents. But for now, we're a little over, but that's all right. I learned a lot. I know you did, Tim.
Yeah, Tuesday nights workshop. You see a lot of this stuff.
That'll be tomorrow. Okay, we hope to see you guys again next Monday morning, okay, for SBAU's Astro Hour number 244. Till then, tell your stargazing friends about us, will you? And always say goodbye like this, Chuck.
Hasta Nebula.
Yo!